Okay, and again, also, it's got the volume turned up. Why would it? No, that's up. Oh, I guess I'm just not talking as loudly. Let's see here. Yeah, I guess so. Okay. All right. Okay, so we're in business. So here's where we were last time. So we were talking about the fundamental theorem of line integrals, right? And again, very, very similar looking to the fundamental theorem of calculus. It functions very often very similarly to the fundamental theorem of calculus. Namely, you find yourself wanting to compute a vector line integral. You can say, hey, I'm going to compute with this formula right here. Very nice. Okay. The way to understand it best, again, I think is sort of different from that. I think the way to understand it best is to view change. Let's see here. So change, namely the right-hand side, as an accumulating quantity. The whole is the sum of the parts, which, by the way, not hard to see. Right? So let's think through, why is this an accumulating quantity? If you have some curve over which you're doing a vector line integral, I make the modest suggestion that the amount the function changes between x0 and x1 and the amount that the function changes between x1 and x2, when you add them up, you get the total amount of change from x0 to x2. Right. Seems like a reasonable suggestion. My own personal favorite point of view on this is to think about how altitude changes as you drive on some sort of a mountain road. So our curved path is the mountain road, and your altitude gain, the whole is the sum of the parts as you drive along that road. Okay. All right. Now, again, once you have an accumulating quantity, and we saw this last time, let me go back real quick, several pages back. Whenever you have an accumulating quantity, reminder, you can view it as being a kind of even if it's not actually a substance, you can treat it like a substance because it behaves like a substance. Right? You can then talk about the associated density. You can talk about the resulting integral theorem. Now, what I have here is an example of how you integrate in 2 dimensions. But, of course, you can also integrate in 1 dimension. You can integrate in 3 dimensions, depending on the context. And you can integrate over curves, any sort of integral where you're computing a whole as a sum of parts. Okay. All right. Let's see here. Here we go. Okay, so back to, here we go. So we just have to figure out what is the corresponding density. In other words, if I'm looking at some piece of curve, now imagine we have some curve going along kind of maybe like that. There's a curve, right? And at this point, looking at, this little piece of curve right there, we have this idea of I wanted to change colors. The position differential, the dx vector. And if you want to know how much does our function change on that little piece of curve, well, we want to know how much our function changes as we displace by that position differential. And we have this long-standing, going back to chapter 2, point of view on how you relate input changes to output changes, right? If you want to know how much the output changes, given dx representing how much the input changes, dot product with the gradient. And that is a hop, skip, and a jump away from our answer because, of course, we also know that dx is TDS, and so this whole thing gets rewritten like so. Now you see we have accumulating quantity per unit size, namely length, along the curve. And so, therefore, our density is gradient dot t. So this is just another, as I like to call them, accumulation theorem. The whole is the sum of the parts, and each part is understood by the associated density, which we now have. And so we put it all together, just like with all of our other accumulation theorems, like so. The whole is the sum of the parts. On each part, we have this density that gives us stuff per unit size, and therefore we have our theorem. So here's the theorem that we were just looking at, fundamental theorem of line integrals. Which, by the way, of course, you can rewrite ever so slightly. Again, TDS is dx, so let's kind of throw those together. And now, just to say it a little bit more conveniently, here then is the theorem that we were just talking about, fundamental theorem of line integrals. Okay. How we doing? Everybody on board? Notice, this theorem comes with a catch. You want to compute a vector line integral, you say. Okay, well, notice that the condition here is if, big if your vector field integrand is a gradient. Very important. It's got to be a gradient. Why does it have to be a gradient? Well, it's just intimately part of the argument that we made. The gradient is part of our density. It's got to be a gradient. Deriving it in the way that we did, it was only an integral of a gradient that we were able to connect to this idea of keeping track of change, accumulating change. So it's got to be a gradient, aka the various terminology for this, but we've already seen, I prefer to call this a gradient. The book likes to call it conservative because of a particular physics application, which is fine, I suppose. You're going to hear that term conservative. It just seems unnecessarily narrow. To me, anti-gradient, I think, is really more directly tells the story. After all, this is the gradient of little f right there, right? And doesn't it then make sense that this is the anti-gradient, right, of the vector field f? Okay. All right, so let's do one. Here we have an example. This is going to be very plug and chug. I am going to pull a fast one on you, and then I'm going to confess to the fast one moments later and refer it to a future later today reference. So here's our question. We want to compute this vector line integral, and the curve is given. Vector field's given. By the way, resist the natural temptation, please. The natural temptation, if you were to see this on an exam, you would be very likely, right, to your first instinct to think, oh, this is a parametrized curve. I should compute this from the parameterization. After all, the parameterization was given. Seems like a reasonable thing to do. And you can compute this from the parameterization. There's nothing wrong with that, except that it's significantly more effort than what we're about to do here, right? So as with so many things in this course, don't think of it as here's how you do them, right? Think of it as tools in your toolbox, and always have your mind open to, oh, yeah, I have a new problem here. Which of my many tools in my toolbox apply to this problem that I'm looking at? Always think about your options, right? See the big picture, and then pick the one that's going to make your life the easiest. So rather than parameterize, notice what we can do here. It's very easily checked, and I encourage everybody to do this arithmetic. But this vector field is easily observed to be the gradient of x squared y squared. Right? Do the appropriate partials. Make sure you see that is in fact the case. So that means that I can use this as my anti-gradient. I can identify, by the way, from the curve itself that, this curve starts when t equals 0, at which point we're at this point, 1, 0. And then let's see, the curve ends when t is equal to pi, and that at t equals pi, therefore, is going to be that point. So I know my starting point. I know my ending point. I have a theorem here that says if you want to compute a vector line integral of a gradient, which I do, which I have, right, then just f of b minus f of a. And so we proceed with the calculation right here. We take our starting point. We take our ending point. We plug into our previously identified anti-gradient function. We use the formula on the previous page. Oh, come on, I wanted to change the color. Our fundamental theorem of line integrals from the previous page. Plug in, compute, answer. Notice I didn't have to deal with any trig to speak of, other than just to identify where the endpoints were. If I had parametrized here, right? If I had followed my knee-jerk reaction, I'd still be halfway through some non-trivial trig integrals. Oh my gosh, look at that x and y are trig, and x and y get squared. I feel like half-angle formulas are probably going to be net. I don't know. It's not looking pretty, right? And independent of whether this one works out pretty, certainly there are cases where it does not work out pretty. So this is a much more desirable method. How we doing? Okay, here's the confession. I totally swept under the rug for dramatic effect, so you can see how awesome this theorem is, right? But what I swept under the rug, where did I dream this up from? It wasn't given. Did I just consult my inner oracle? Right? How, more to the point, will you, in practice, find these anti-gradient functions? Right? Pretty important. So there is a method for how to find anti-gradients, and I will show you. And it's pretty algorithmic and pretty straightforward. It's not that bad. We'll get to it in half an hour, something like that. No problem. So anyway, that's the sort of the remaining what I owe you to, in some sense, complete this example. Is how did I dream up that critical part of my solution? Okay. Alrighty. So before we do that, I want to talk about some other ideas. Path independence is a really big one. I'm going to make here at first a fairly modest statement that if you want to compute a line integral over some curve, right? You got some curve. The curve matters. Right now, again, of course it does, right? The curve is what tells me where I am, and thus what I will be plugging into the vector field that I'm clearly going to be doing computations with, right? The curve tells me at said points what is the velocity vector, the displacement differential, the unit tangent vector. How do I get my hands on the question of which direction is this curve going and how far do we go in each step? That all comes from the curve, right? So of course the computation depends on the curve. Everything in this computation depends on the curve. So with that in mind, obviously the curve matters. It is an eyebrow raiser when someone suggests that for some vector fields, only the endpoints matter. Right? The natural reaction to this would be say, come on, get out of town. There's no way. Clearly the curve matters. Right? Nevertheless, it's really weird. It's really surprising. There are some vector fields, and I emphasize this is a property of the vector field. There are some vector fields where when you're doing the line integral, the curve doesn't matter other than where the endpoints are. So as long as you have agreed upon endpoints, right? If you're doing a vector line integral of some vector field, if you choose on the one hand one curve that starts and ends as required, and another curve that starts and ends as required. Again, there are these special vector fields, amazingly, called path-independent vector fields, whose vector line integrals couldn't care less which curve you pick. All the curves don't matter. And again, how could this be? Look, in the whole integral, when you write down the Riemann sum, right, that you compute these integrals from, every step along the curve depends on the curve. So very surprising that this would be the case. Now I emphasize, this is really, really important. A very common mistake that students make is they think or act, at least in some cases, like they think that this is just a new trick that you're allowed to use for all vector fields, and very importantly not. Very importantly, this is only some special vector fields, right? Most vector fields, this doesn't work at all. And just to make that painfully obvious, here is an example to the contrary. So I'm going to look at this as a starting point and that as an ending point. And we've got a vector field here. Let's see here. I'll do it like this. This vector field, you can persuade yourself, looks kind of like this. There, and now let's just think it through. How would I compute these? I've got this curve C1. I've got this curve C2. I'm going to compute their line integrals, at least qualitatively, and we're going to observe that they're different. Of course, they're different. They're different curves, right? So here's the computation. Let's think about this first curve here, C1, like so. Compute that line integral. Along this first chunk, the vector field is 0. So obviously along that chunk of C1, the integral is 0. Along this chunk, the sort of the top edge of that little square that I made, along there, notice the vector field is pointing up. Let's see, up, right? But the dx vectors are all pointing horizontally. So f dot dx, well, that's a dot product of two vectors that are clearly orthogonal, and so that's 0. So on this green curve, clearly the line integral is 0. I don't even have to do any algebra I guess I have to do the dot product. Okay, well, fine. Now let's just think through this second curve here, this C2. How do I compute that integral on C2? Well, let's do the same calculation, and just to clear up the clutter, let me get all that out of the way. And in fact, I don't really need that in the picture either. Let's think through this. What's going on here? Well, again, on this bottom chunk, the vector field is up. The dx vectors are to the side. Again, that's orthogonal. Again, that dot product is 0, so I get 0 there. But on this chunk, the vector field is up. The dx vectors are up. The fluid is clearly flowing along the curve. In fact, not only to some extent, but completely, perfectly along the curve in a clearly positive manner. And so altogether, this vector line integral is clearly positive. So again, the only goal here was to just emphasize how, of course, these should be expected to be different. So please don't make the mistake of just treating all vector fields as if they're path independent. It absolutely does not work. Most vector fields are not path independent. Okay. All right, so this seems like an exercise in silliness, doesn't it? Right? We're sitting here talking about some property that we have yet to see exists at all, and we seem to have a pretty compelling argument that we should not expect it to exist. So let me show you an example where it does. In fact, this is an entire category of examples showing that this really does happen. And in particular, it happens when you're talking about gradient fields. If you're looking at gradients are path independent. We got to worry about regularity, so continuous, right? We're not going to get upset about that kind of thing in this class. Gradients are path independent. Now, here's why. Keep in mind, path independence suggests that if you have, let me use a different color here. If you have an agreed upon starting point, and an agreed upon ending point, that you should be able to pick any curve and you would always get the same answer. Okay, well, let's think about this curve C1 here. How would I compute this integral on C1? Oh, sweet. I'm looking at an integral of a gradient, which means I can apply the fundamental theorem of line integrals. Because that's what the fundamental theorem of line integrals does. It computes integrals of gradients. So there you go, boom. Okay, now let's think about a different curve. What about C2 here? Now, again, very importantly, notice, same starting point. That's important. Same ending point. That's important. That's part of the deal. Path independence only addresses changing the curve in between the fixed starting point and fixed ending point. So anyway, that noted, we have a new curve here. How would I compute this integral? Oh, well, hey, sweet. Check it out again. I'm computing a vector line integral of a gradient. That's what the fundamental theorem of line integrals does, right? And so we compute that. And of course, now I've got these two different integrals. I need to decide if these two integrals are the same or not. Well, they're computed with the exact same formula, computed at the exact same starting and ending points as arranged. So yeah, they're equal to the same thing, and therefore they're equal to each other. Everybody good with that? And this will work whenever you're looking at it's got to be continuous, and again, regularity conditions are sticky sometimes, but not our focus. Gradients are path independent. So I think this is really interesting. It's such a surprise, especially after you see such easy examples suggesting that this is a really unnatural thing to expect. When things that are unnatural to expect turn out to be true, that's amazing. Okay, now another true fact, not only is every gradient path independent, but also every path independent, again, regularity issues, every path independent vector field is a gradient. So this goes both ways. In the category of appropriately regular vector fields, path independence and being a gradient are simultaneous. The proof of this second fact, the argument of how you would see it if you want to look a quick outline, then take a look at this. It's just a quick sketch. You're not responsible for it. You don't need to, but if you're curious, roughly speaking, we just literally compute the anti-gradient by a clever observation. But you don't need to worry about that. Okay, here's a different way to say path independence. Keep in mind, the idea of path independence is that with start and end points settled, that the green line integral should always equal to the blue line integral. And now I'm just going to make the observation that, okay, well, nothing happens if I subtract over to the other side of the equation. That's piddly. Right? So now let's look at this difference, and I'm going to point out that difference is actually another line integral. If I were to think about the following curve that starts with C1, it moves along C1, and then when it gets to that point, it keeps going and goes backwards along C2 till it gets back to the original starting point. How would I compute that orange line integral? Well, I'm going to be computing exactly the integral on C1, and then kind of the integral on that same curve C2, except with the opposite orientation, namely I'm going to get minus the integral of C2. And so that orange integral is exactly what this is. So another way to say that green equals blue is to say that orange equals 0. Is that cool? So, so this is this alternative formulation. You could take this as an alternate definition, I suppose, that path independence could be defined as, could be viewed as, closed line integrals must always be 0.
Does F have to be a gradient for that to work?
Well, F has to be path independent. This is a definition of path independence, and as we saw previously, path independence is synonymous with being a gradient. So yeah. So think of this as an alternative property of gradient fields. Yeah. But I'm going to refer to this as path independent fields because that's where the immediate connection is. Yeah. Is that cool? Yeah. Good. All right, so here's a fun little sort of visualization, you might say. I don't know how familiar y'all are with the art of this guy named M.C. Escher. It's from, I don't know, like 100 years ago or something. I'm not up on the dates, but his art is fun in various ways. He had several phases, and he's done various different things. But one of the things that he did is draw very realistic-looking physical impossibilities, right? So you look at this art here. This is a drawing of some people walking along the stairs on top of a building, and it's kind of ho-hum and yawn. Whatever. Yeah. Okay. People walking. They must be in trouble. They have to walk 500 laps around the roof for punishment. It seems sort of silly, right? But then you start to notice, wait a minute. These people that this character is following, they're all walking uphill, and then they turn to the right and continue walking uphill, and then continue walking uphill, and then continue walking uphill, and then somehow get right back to where they were in the first place. What's going on there? That doesn't, wait a minute, is that pop? That doesn't sound right. Right? So that's pretty cool. So he was, I don't know first, but he was one of the famous people anyway who realized that this is kind of a brain scratcher and fun to put into artistic form. Okay, so one way you can react to this art is to say, weird, right? This being a math class, I'm going to react to this by trying to write down mathematically what the problem is, right? So I'm going to observe that if we were to just look at the gradient of the altitude function. Altitude's a function of position on the roof of this building, whatever. And so I'm going to call this the steepness vector field because, of course, y'all remember from long ago, gradients always point uphill, and the magnitude tells you how steep the graph is, right? So I'll call this the steepness field. Well, it's clearly a gradient. We just saw that gradients are path independent. Path independence means closed line integrals are equal to 0. Okay, well, wait a second here, though. This line integral, that of course has to be 0. In some sense, the whole point to this picture is that when you look at gradient.dx, you're keeping track of the little altitude changes that are being made. Each step that's being taken, right? F.dx is keeping track of how much altitude changed. And if you add up all of these altitude changes as drawn, right, going along, the art would suggest that we're adding up a bunch of positive things. How can we add up a bunch of positive things and get 0? Right, so this is a mathematical formulation of why Escher stairs are impossible. That makes sense? So, got it, cool. All right. Okay, so why do we like path independence? For whatever it's worth, path independence is a very conceptually important idea. You can use the idea of path independence to make certain observations about how potential energy works in physics. And, again, I would love to digress and talk about that. It's not really the focus of this course, and so I have to restrain myself. But nevertheless, it has very nice conceptual interpretation benefits. In fact, we just saw one, right? We did an artistic interpretation based on path independence. So let's talk instead, though, about the extent to which, to what extent is path independence useful computationally? Okay, well, I mean, I guess, but look, let's make the observation. If you have a path-independent vector field, as we just discussed, it's a gradient. If it's a gradient, just use the fundamental theorem of line integrals, right? So there's a point of view that says computationally, it's not so much of a, how are we going to benefit from this computationally? How are we going to, it's like we already had a screwdriver, and now we have a different brand of screwdriver. Yeah, I already had a screwdriver. This helps me address the exact same category of questions that I already could. So that is a tempting argument. It's mostly true. There are some counterexamples because, of course, to use the fundamental theorem, you need to find the antigradient, and sometimes finding the antigradient is hard. So it involves doing some integrals. Integrals can be hard, and in such cases, the fundamental theorem is not such a great option. So let's just look anyway then at how we can actually use path independence to actually compute something. In particular, we're going to look at this integral right here. Notice again we have a vector field given. We have a curve given. How would I compute this thing? And of course you can parameterize and plug and chug. Again, it's going to get undesirable. We can find an antigradient, and in this example, yes, absolutely. I bet you could probably, invoke your cleverness and probably come up with what the antigradient is. I'm sure you could. I'll just remind you, even though in this case you can, there are certainly some cases where you can't. And so let's ignore that option. And let's just consider how to use the path independence. So we're given here in the statement of the question, given that this vector field is path independent, how can I use that? Okay, well, I've been asked to compute the integral on that green curve. Path independence says that I can, as long as I tie down the starting point and tie down the ending point, I can use any curve I want. Go crazy. I could use this curve if I were so inclined. I don't think I'm so inclined, but I'm free to do so if I want. Right? So let's think creatively. What curve can we think of that would be more desirable? It's got to still start at that point. It's got to still end at that point. But what's a more desirable curve than this green, top half of the unit circle, which, by the way, take your pick. You're going to be dealing with trig or square roots. Choose your evil, right? Well, I like that curve. Nice straight line. Path independence says I'm perfectly welcome to compute on this blue curve instead of this green curve. So I tell you what, I'm going to do that. I'm going to say, you know what? Phooey on the green curve. I don't even like that curve. Right? Invoking the path independence, I'm going to use this blue curve, which is easy to parameterize. To it. And then you can plug and chug. Now, in addition to plugging chugging, let me point out, that curve is way easier to parameterize. So we've already saved ourselves loads of effort just by choosing cleverly a much more desirable curve. But it's even better than that. Because check this out. You can see right here, don't forget that when you parameterize, these are your x and your y, right? So my y coordinate here, I can see right there, is 0 on this entire blue curve. And of course, this calculation is only happening on that blue curve. Y is in fact 0. Okay, well, which means that this whole term, wrong color, which means that this whole term right here is just 0. That's nice. You can also notice, and take your pick on how you choose to see this, but our dx vector, there's something really nice about our dx vector. Keep in mind the dx vector represents displacements along our curve. Now our curve being this new one in light blue, the dx vectors you can see are all horizontal, right there in the picture. So, being horizontal, dy is 0. And it's all fallen apart at this point in a good way. You see we've got this down now to an integral of 0, which is 0. So bing, win. And again, we saved ourselves loads of effort. Everybody good? Okay. All right, now here's another confession. I again, for dramatic effect, swept something under the rug in this example. I just had it given from on high that this vector field's path independent. How are you going to know that? Are you going to rely on, somebody to come up in your future applications of multivariable calculus and just say, hey, by the way, that vector field's path independent, go ahead, right? No, of course not. So you're going to need to know how to identify when is a vector field path independent, and so let's talk about that. There's a lovely little idea here. Let me just go right to the result, and that is a vector field being a gradient, namely a vector field being path independent. And again, regularity issues, I don't want to get bogged down in regularity issues. Technically, we need this to be a C1. Anyway, it doesn't matter. This is always simultaneous with what I call a local test. This is the local test. The curl of that vector field is 0. Real quick, why do I call this a local test? If you were to ask first about this condition, vector field being a gradient of something, notice the way I would satisfy this has to be the same little f, that same function little f, for everywhere in the domain. So that's what I'm going to call a global condition. On the other hand, computing the curl. Well, you compute curl with a formula that involves derivatives, 1 point at a time. So local in the sense that this curl can be computed at any point independent of what's going on at any other point. So anyway, whatever that's worth. All right, so how do I know this is true? This claim, and by the way, let's notice how awesome that this is as a result, because if I want to know if I'm dealing with a gradient, if I want to know if a vector field is path independent, apparently all I have to do is compute the curl, plug and chug, and see if you get 0. Simple as that. That's very doable. And so this is how we're going to determine whether something's path independent, aka a gradient, in practice very often. The way we see this, again, this is the connection I need to make. I'm going to first point out that we already know these 3 things are true. Right? Or excuse me, we know that these 3 things are equivalent. If we had, in fact, a gradient, it would be path independent. It would therefore have all closed line integrals. All circulations would have to be 0. So I know those are true. Now I'm going to make the observation that Green's theorem, in fact, allows us to immediately connect circulations to double integrals of curl. That's just straight up what Green's theorem is. Right? So when I say that the closed line integral is always 0, I am in effect also saying that these double integrals are all 0. Okay, and now let's entertain that. How could it be? How could it possibly be that double integrals of curl are always 0 for every domain? No matter what domain you pick, any domain, curl is always 0. How could that be? what functions can you think of as integrands, where the double integral is always 0, no matter what domain you pick? Now, I'll bet you can't think of any continuous integrands for double integrals that are always 0 for every domain other than this function being, in fact, just flat, always 0. Know what I mean? Does that make sense? Okay. All right, so that's the argument. It's a real clever little argument, and this makes for a fantastic test. Real quick comment on language. I like this terminology. I did not make it up. It's standard terminology. Such a vector field is called irrotational. Keep in mind that curl is a way of getting our hands on the rotational aspect of the fluid that the vector field is describing. Right? So, ir being a prefix suggesting something like non, right, is what communicates the idea that, that we can't have any rotational aspect. In other words, that the curl has to be 0. So I think this is very natural language. I'm a fan. An irrotational vector field is a vector field whose curl is 0. Now, by the way, let's do a quick count of terminology just for fun. How many words do we now have to describe these vector fields we're talking about? Well, they are gradients. They're gradient fields. They're path-independent fields. They are, we see now, irrotational fields. And then, of course, many people, like to call them conservative fields. So that's confusing, isn't it? We have 4 different words. They're all talking about the same vector fields. And heads up. Right? So now, if part of your job then is to make sure that you remember not only what all these words mean, but that whenever you hear any one of those words, you get to infer the others. So if somebody tells you, "Hey, I have a path-independent vector field," oh, that means it's irrotational. Right? Or if they tell you, "Hey, I have a conservative vector field," oh, conservative, that means it's path independent. That means it has an anti-gradient. Right? So the terminology, again, you just have to, it's annoying that we have these 4 words. For whatever it's worth, 2 seconds, I will point out that while they're ultimately all the same vector fields, 3 of these are at least describing different properties of these all the same vector fields. This is talking about how the fluid is rotating. This is talking about the relationship with the gradient operator. And this is talking about how the integral changes when you move the curve, but not the endpoints. So they are different properties of the same vector fields, but nevertheless, it's 3, 4 words describing the same fields. Yes?
The last connection between the double integral curl to
Yeah.
curl f being 0, that's not if and only if, right? So basically saying that if a vector field is irrotational, then it must be path independent. But if it's path independent, it doesn't have to be irrotational.
It does. Yeah, no, this is if and only if, because a key point here is that because the vector field is C1, that means that this vector field, this function, I'm sorry, I got it wrong way. If this is C1, right, that's C1, that means that this derivative of it is continuous. And if you have a continuous function where the double integral is always 0, in fact, that function must be 0. Yeah, and exactly why that, you have to think through, if it wasn't, if you had a non-zero function where the double integrals are always 0, wherever your function is non-zero, I'm going to do a double integral right under that area, and I'm going to get a non-zero integral.
Oh, and this is we're talking about any domain D.
Yeah, exactly. That's right. So the point is, this is true, right? If we say we have a path-independent vector fields, that means that this path independence applies everywhere, and so yes, for any D.
Okay.
Is that satisfying?
Yeah, that makes sense.
That's good. Good. Okay. Okay, good news. There is an analogous result to this in 3 dimensions. Note what we were just discussing is only in 2 dimensions. What I'm claiming down here is in 3 dimensions. The argument, however, this argument that we made here, we don't yet have the necessary tools. Whoops. We don't yet have the necessary tools to be able to make this argument. We will actually pretty soon. The next few days, I forget exactly. Same result. The argument will come later. But yeah, yes.
So the expression on the right, the del cross f.
Yeah.
That's also referred to as del f.
Yeah, I know, and exactly. That's a great point. Let me talk about that for a second. This is called curl of f, and this is also pronounced curl of f. They are different, though. Notice, for one thing, this is just a scalar. This, however, is a vector. So they are structurally different things, but they do play analogous roles. In fact, you can start to see how they play analogous roles right here. They serve as the local test in morally equivalent ways, just in these 2 different contexts, 2-dimensional versus 3-dimensional. So that's an argument for kind of lumping them together with the same terminology. But yeah, it is a little uncomfortable, especially given that this notation where you use del cross, that is only in 3 dimensions can you write that, right? In 3 dimensions, you can also write the word curl, just like that. But the del cross you can only do in 3, not 2. So yeah, it's a little weird. Is that cool? Yeah. All right. Okie dokie. Quick example. Here's a vector field. Let's try to decide, is this a gradient? And you could sit there and try to play games with, consulting your inner oracle, trying to figure out, trying to find the anti-gradient explicitly, and you play around. And I'm going to show you how to do it in a minute, but there's a much easier way to answer the question very immediately, just by recalling that we have our test. You want to know if a vector field is a gradient? Compute the curl. See if you get 0. All right, well, here's the curl. By the way, I didn't do a good job there, did I? There we go. Compute the curl. Notice I didn't even finish the computation. I only computed the first coordinate of the curl. And I can already see that this is not going to end up being the 0 vector. Clearly. Let me do that in a different color. We clearly do not have 0. The first coordinate's non-zero, therefore the vector can't be 0. And if it's not 0, then that means that this is not a gradient. Is that good? Just to emphasize the obvious, this business about only having to compute the first coordinate, that's only if you get not 0, right? Let's imagine some hypothetical, right? Some other vector field, something different, where your first coordinate of the curl, let's suppose you did get 0. Well, if that first coordinate is 0, can you conclude that the vector is 0? Well, no, because these 2 things could still go either way, right? So you only get to save effort if you don't get 0. So anyway, careful with that. You don't want to accidentally make that boo-boo. It's surprisingly common. Okay. Another example. Let's decide, is this vector field a gradient? So we play the game. This is, you'll notice, 2-dimensional. Vector field's 2-dimensional. We look at the 2-dimensional test. It says compute the curl, see if you get 0. Okie dokie. So we compute the curl. We did not get 0, so this is not. So this is not a gradient. Is that cool? The reason I like this example is because, in addition to being sort of algebraically explicit, this also tracks with some clear geometric intuition. I think this is a good thing to. It's one thing to know that something is true. It's another thing to have some sense of why it should be true, right? So I would like to point out, we would be pretty uncomfortable if someone was going around claiming this is a gradient. Then they're saying that this vector field here is always pointing uphill on some graph. Really? All these vectors are pointing uphill? That's all uphill. I just went around in a circle going uphill the whole way and got right back to where I was in the first place. This is basically a Escher stairs nonsense. Yeah? All right. Okay, so, so there's some really wonderful facts about these vector calculus theorems that we're doing here. This is deep water. I'm not going to be able to tell you anywhere near the whole story. It's too sophisticated. It's too deep. But these underlying deep realities have some nice, I'm going to call them kind of shadows, manifestations in areas where we can absolutely, totally not only make sense out of them, but benefit from them. In fact, we benefit from them computationally. This is actually really powerful observations. This isn't just mathematicians having fun. So what I've drawn here is I'm calling this the strategic diagram for 2 dimensions. I have a better image of this typed out. This is from my textbook. So the typesetting has the advantage that you can include more stuff with more detail. It's just easier to read. So, by the way, this diagram is called diagram.pdf. It's in the course resources folder, I guess it is, on the website. So you could, wherever it was that you downloaded the lecture notes, this is in that exact same location. Feel free to take a look for yourselves. So I want to point out what's nice about this. You will recall from Chapter 3 that I previously said that if you compose the gradient operator with the curl, which here I referred to as Green's operator. Again, that just means curl. Then I just vaguely said good things happen. And this diagram I'm about to talk through is showing a lot of these good things. It organizes in a very convenient way a lot of the sort of the convenient punchlines. So one of them we've already talked about, and that is that when you compose, you get 0. More to the point, everything has a lifetime of 2. And so, neat fact, if you have a function and you compute its gradient, you get some vector field, well, then Green's operator will give you 0. It was born, it survived, it died. Right? Lifetime of 2. Recall also, if you have some vector field and Green's operator, if curl, in other words, is 0, remember, everything has a lifetime of 2. That means that that vector field must be, in fact, the gradient of some function for this story to represent a lifetime of 2. Right, so this is kind of a diagrammatic shorthand for what we just saw as our local test, right? If a vector field is irrotational, then it's a gradient. That's when it's just a, for whatever that's worth. here's another thing. Let's talk through our big theorems that I've got represented down here. And by the way, this diagram is set up in such a way that boundary goes like this. Notice, of course, if you have a two-dimensional region, its boundary you should expect to be a curve. If you have a curve, its boundary you would expect to consist of a starting point and an ending point. Right? And then it turns out, again, deep water, take my word for it, that good things happen if we evaluate like so. So, for example, if you come to me with a function and a two-dimensional region, double integral is, I'm going to call the natural. Again, just take my word for it. There are really good things are going to happen if we agree that this is what we mean by evaluating a function over a region. And then likewise, vector field in a curve, we'll do vector line integrals, et cetera, et cetera. All that said, let's think about what Green's theorem says. Remember, we talked about Green's theorem last time. And that says that if you have a region and you look at its boundary curve, if you have a vector field and you compute the curl, right, then, well, let's see here. The line integral of the original vector field over the boundary curve and the double integral of the curl over the original region, Green's theorem says that these are zero. Are equal, excuse me, sorry. Difference is zero. Anyway, these integrals are equal. So just as a diagrammatic, just to kind of see what Green's theorem kind of looks like on this diagram, the idea is that if you push forward with your functions and vector fields, and if you kind of push, the direction boundaries go, and if you evaluate in these senses, then you get the same thing on both sides. And what's weird is the fundamental theorem of line integrals has the same exact pattern. If you look at a gradient, if you take a curve and look at its endpoints, plugging in the endpoints to the original function, doing a line integral of the gradient over the original curve, equal. So I think it's pretty wild, right? These are two totally different theorems, and yet the way they sort of manifest on the diagram is the same exact pattern. That's weird. It's an eyebrow raiser. This makes you wonder if maybe there's something going on underneath that's making this happen. I mean, is this a coincidence? Doesn't seem like a coincidence, does it? So in fact, just to let you know, there is a, again, this got figured out in like the 1930s or something, right? It was not that long ago in the big scheme of things. In fact, there is a single theorem, the generalized Stokes' theorem, they call it, that has various special cases, and the generalized Stokes' theorem in this context is the fundamental theorem of line integrals. And the same exact generalized Stokes' theorem in this context is Green's theorem. And the same exact theorem in other contexts will be other theorems that we're going to be seeing. So what we're seeing here is a kind of a glimpse. The fact that these patterns are exactly the same, we're seeing little glimpses, kind of shadows of this much more powerful, sophisticated, deeper, bigger theorem that, again, unfortunately, beyond the scope of this course. But it's good to notice the patterns. Right? Once you realize that there's a pattern, now you don't really quite so much have two separate theorems to learn. You have one pattern to learn. Everybody see what I'm doing there? Okay. It's also going to be beneficial, we'll see this later on, to note how our special vector fields show up on the diagram. So the special vector fields we've talked about are gradients. Gradients for which there is a function whose gradient is that vector field. So this is how I'm going to, on the diagram, represent the feature that these special vector fields are gradients. Now, these Same vector fields, recall, are irrotational. Green's operator gives you 0. Same vector fields that we're talking about. Different features, these different features demonstrating, sort of manifesting differently on the diagram. And then what about path independence? Now this is how I like to write down path independence on this diagram. Path independence says that if you have two curves with the same boundary points, that you should get the same value for the line integral. So that's how that looks on this diagram. This is just a little bit of foreshadowing. This observation about how path independence and its various equivalent features look on this diagram. This is going to be very useful to us in a few days. Next week, I guess it'll be, as we're doing some other big theorems. So we're going to see this again. Okay, so how do we find antigradients? This is very plug and chug. I'm going to go through this pretty quickly. It's not such a deep idea. In fact, if you have a vector field that is a gradient, right? Let's suppose we have a vector field that's a gradient. Well, I can just write that out in coordinates. In coordinates, there's my vector field, and that's what a gradient is, which means that I need these three things to be true. Now, those three things are pretty much equivalent. I'm going to commit a little math crime here, confess and fix it later, but roughly speaking, fix to come later, are equivalent to these three statements. Let's just kind of talk through them. This says the x partial of f is p. This says f is the x antipartial of p. They're the same statement. It's like one's active voice, the other's passive voice, right? But they're the same. F is the thing whose x partial is p. So the x antipartial of p is f. Is that satisfying to everybody? Morally, kind of the same statement. Now, let's fix it. Whenever you do antiderivatives, there's always an additive constant. Y'all probably expected me to put a plus c at the end, right? Let's remind ourselves real quick why we say plus c. And it's because anytime you add a constant, you're not changing the value of the derivative, because after all, the derivative of that constant is 0. So you're not changing the fact that this equation works if you just add a constant, because its x partial is 0. And now I extend further and to say, all right, well, in fact, constants are not the only things whose x partials are 0. Any function of only y and z, the x partial is still 0. In other words, any function of only y and z is still free to add in, and it doesn't affect the fact that that antipartial works. Okay. All right. So here's what we really have to do then. And this looks like bad news, but if you want to find this antigradient, right? How are we going to find that antigradient? Well, I'm going to have to compute these three separate things, and I need them all to equal to the same function, which seems unlikely. Keep in mind, though, that I get to pick these functions however might be convenient for our purposes, as long as this only depends on y and z, this only depends on x and z, this only depends on x and y. So let's see this in action. It's just a very straightforward process. Here is a vector field. I want to find an antigradient. Notice I have a P, a Q, and an R. Per the previous page, P goes there, Q goes there, R goes there, just following the rules. We take the anti-partials. This is just single variable calculus, basically, right? Anti-partials. It's just anti-derivatives, but with partials. Nothing to it. Everybody on board so far? I mean, the little details. Make sure I didn't mess up the execution there, but. And don't forget to add in your partial constants. We call these partial constant functions. So when I ask if these are all equal, now it's tempting and false to think that we need for these three to all be equal, which obviously they're not. But again, that's not the deal. I need these three things all to be equal. And I'm allowed to make these C1, C2, C3 any functions that might be convenient for my purposes. Okay, well, how about this? I feel like if I were to make this x squared y, now I've got identical terms in all three of these expressions, and that's starting to make them look more equal. And then likewise, if I were to make this C2, if I were to make that xz, well, now check it out. All three of these things that need to be equal, yeah, they all have that blue term as well. And then if I were to likewise look at that, and then choose to make that minus yz squared, then again, all three of these functions indeed are equal. I have found a single function that satisfies all three of my requirements, and so I have found the anti-gradient. Everybody see how the game is played, right? It's a little game, right? Every vector field represents a kind of a game board, and you play the game, and you see if you can win the game. Right? So that's all there is to that. Okay, now note it will not always work. Sometimes you will lose the game. As well you should. After all, this is a question. As to, you can't just assume that an anti-gradient always exists. Most vector fields, again, are not special. They are not gradients. They're not path independent. They're not, right? These are special properties. So in most cases, there is no anti-gradient. So let's see how this shakes out in such a case. We already know this vector field failed our test. So this is a typo. Good night. Shame on me. I meant little f here. Sorry. Typo. There should be no anti-gradient. We already know the vector field itself is not a gradient of anything. So we should lose this game. Let's see how the game looks. Again, here are the integrals to be computed. Here are those anti-partials. Don't forget your partial constants. The question then is, can I find ways to select C1 and C2 that make these equal? Is there something I can put here and something else that I can put here that makes this work? Keeping in mind that in green, only Y's are allowed, and in blue, only X is allowed. And I think you're going to notice pretty quickly as you try to make that game work that you're going to lose that game. This game is rigged against you. You can't win. Yeah? Okay. All right. Okay. Now we're done with Chapter 6. Moving along to Chapter 7. So just a reminder, when we started Chapter 6, we had to spend the first little while of Chapter 6 defining some new constructions. We had to define what we mean by a scalar line integral and a vector line integral, and we had just the mechanics of how do you define them, how do you compute them, what else? How else can you write them? What are the little tips and tricks for how to compute them? Right before we could get into fancy theorems like the fundamental theorem of line integrals, and Green's theorem, and before we could get into the powerful ideas, we had to develop some machinery. So here we are again in Chapter 7, and I'm going to have to develop some machinery here. This is just things that have to get said. tools that we're going to be working with. Y'all remember parametrized curves? Here's an idea called a parametric surface. And it's a massive ripoff of the idea of a parametric curve. It's just position as a function of not one variable, not one parameter, but now two parameters. So an easy first example, notice here we have position in R3 written as a function of two parameters, S and T. So instead of position as a function of one parameter, and that one parameter sort of tracing out a one-dimensional curve, here we're going to have position as a function of two parameters. The parameters allow us sort of two different directions that we can go, thus kind of creating a now two-dimensional, not a curve, but now a surface. Does that make sense? So in this case, let's look at the specifics. The specifics are if you start at some point in the plane, and if you have a couple of direction vectors v1 and v2 that are given. So I'm looking for the plane that goes through that given point and that's parallel to both v1 and v2. How would I generate all these other points, right? How would I generate this other point from x0, v1, and v2? And I hope it's not too terribly surprising that, well, look, I'm just going to need to go to some extent in the v1 direction, and I'm going to need to go to some extent in the v2 direction. And wherever you might need to get to in this plane, if you've got two different directions in which you can move as much as you like with your parameters s and t, yeah, you can get there from here, right? No problem. So this will generate all the points in the plane. By the way, flashback to section 1.5. You may recall there was a homework exercise that used this construction, kind of like this. So anyway, for your reference. Okay, here's another example of how to create a parameterization. This one's also familiar, I hope. Y'all remember the graph parameterization for curves? If a curve is a graph, you follow a certain rule. You let the input variable be the parameter. Very similar deal here. If you have a surface that is a graph, right? One of the variables is a function of the others. Then you let the input variables, plural, be your parameters. And everything just works. Works perfectly. Easy example. How would I parameterize this paraboloid? Right, y'all remember paraboloids? Well, check it out. It's a graph. My input variables appear to be x and y. So per the instructions here, I'm going to let x and y be my parameters, s and t. And if that's the case, look, if s and t are x and y, and if x and y compute z, then that kind of forces me to make z s squared plus t squared. Just like we did with parametric curves, the graph parameterization for curves. Same sort of thing here, parameterizing a surface. Okay, and looks like we're out of time. Yeah, I'll pick up here on tomorrow. All right, see you later. Have a good one. And real quick about